Hello, hello. Welcome back to the lab. Much like in our previous video, I want to circle back on something. This time, instead of the instead of the battery daughter card, I want to tell you a little bit more about our inverter. So, this daughter card is even more simple than the previous one, if I'm being completely honest. We've got the micro, which runs the control loop and does everything. I mean, that's all this card does. It runs a real-time control loop. And so we're running this control loop. We've got the fan control over here, and then the rest of it is really on the other side because it's all power. But we've got gate drivers, current sense amps, and a voltage monitoring circuit. Now on this side, we've got two gigantic custom inductors that should be able to handle 2400 watts out. Then we've got two sets of FETs. We got 4 giant FETs that we're using to drive the inverter. Now these are the FETs that were exploding. And what I did is I slowed down the gate drive of the high side FET. That helped a lot. I basically incrementally tweaked the gate drive until I could install it in here without the FETs exploding. Yeah, so we had to buy a couple more FETs, but that I don't mind, that's okay. So basically what we've got is we've got the core output. We've got the core output here with the filter cap and the input capacitance. These are film caps, by the way. And then basically it goes through a fuse, through our current monitors, one on the top, one on the bottom. We're using some internal layers, no worries, it's connected with plenty of copper. Then we've got an output EMI filter and an ICL, which is basically just a transient limiter for the output, a little bit of assurance there. And then of course we've got a screw-based, very beefy output that actually screws into the board. I like this connector a lot. So that's about all she wrote. It's a pretty standard inverter. Now, and this is a single level inverter, it's not a multi-level. That's important, it's an important distinction. Basically just means there's one totem pole of FETs on each side. If this were a 3-phase, it would have 3 sets of FETs instead of 2. Now, the reason why I'm setting this all up like that is because there is a problem. There's a problem with those FETs, and that problem is that the control loop wasn't really working, and based on what I saw coming back from the daughter card, it almost seems like we were getting a DC level back where we should be getting an AC level. That was a little weird. That was a little weird to me. So what I've done for our debug today is I've added a couple wires. And we're going to probe around a little bit and see if we can't figure out what is going on. Yeah, so the problem that we noticed was on the output of the isolation amplifier. Just so you guys know, we've got both circuit ground and chassis ground tied to earth ground through our power supply, which is unplugged. Ooh, I should probably plug that in. Okay, so now we are effectively earthed. That's important to remember because this is also earth ground. If we put this clip in the wrong place, it might be a bad time. Okay. So first things first, we're going to start on the low voltage ground side. We're going to connect straight to the output of the isolation amplifier. Okay, so we should be expecting to see about 3 volts peak to peak from that signal. So if we power down, it's booting. And if we kick it on, A horizontal scale is 10 milliseconds per division. We should have seen a sine wave. But yeah, it looks like we're just getting a DC level. Actually, it looks more like we're just getting noise. Okay, that's not super. Let's wait for the DC bus to die down. Actually, wait, let's test that one more time. Our main board is staying alive. Okay. I must have had some math error going on because I moved literally the same command to a slightly different location in the code, and now it works fine. So, alright. So we should be making a sine wave that is the full amplitude of the DC bus. We would expect to see 180 some volts DC being chopped up in a sine wave, which would turn into like, I don't know, 160, 140. Mental math is hard. Looks like the RMS is not being calculated, but that looks exactly correct. Looks like we're seeing 180 volts in that sine wave. That's pretty cool. So honestly, it looks like the mainboard micro is still running. It just looks like our display is dying, which either means the clock frequency isn't right, or just that there's too much interference on that cable. Might just be that there's too much interference on that cable. But this looks pretty cool. Okay. So now that we have a sine wave, and we know that we have a sine wave, let's take a look at what that feedback looks like. We've booted. Let's try that again. There we go. So now we saw it for real. It's really just noise. Noise is what we're seeing on the output of that DC bus. Looking at what's on the high side of the isolation amplifier. Yeah, that pretty much also noise. On the real scope, I can see a preview that is very realistic, where I'm seeing the trace of the waveform just surrounded by noise. But yeah, we are well below the noise floor. And so a big reason why I think that has to do with our layout. Basically, I snuck some of those sensing lines underneath the mains output, and I think we're getting a lot of that switching noise coupling into our sense line. And since our switching noise is, 200 volts peak to peak, I think even a very, very small amount of AC coupling out of that sense line, because it's being triggered by, or being driven by, 2 meg resistor. Yep, we've got a pretty high impedance net to reduce power consumption, and then we've got a bunch of noise coupling in, and we don't have a very good ground reference because we've basically got mains coming out. Now, if we flood our ground reference, our high voltage bus, on this entire mains output, we might see a very different story. And I think, honestly, this might take another rev of the daughter card. We might need to go up to a 6-layer board to make this inverter really work. I can't say that for sure, but we'll either need a 6-layer board or maybe a cable harness that comes up to like the top part of the board so we can route it better. 'Cause right now we've basically got a tunnel low voltage on the internal layers of the board. If we could remove that to get our current sense, I don't know. There's a couple different things we could try. But we'll need to cross that bridge another day because I think it'll take a hardware revision. I think it'll take some tweaks to really get this going. We have basically this isolation amplifier on a dev board. I could try to tack off the critical signals, tap off line, tap off neutral, feed it through the external board, get it further away from the interference, and feed the input back in. So there's ways that we can use this to like breadboard the rest of the design, but it looks like we might need another rev of this daughter card specifically. Now that we got the battery daughter card tuned, I mean it's a little big, but like it seems to be working just fine, no problems. So that's awesome. But yeah, we could stand to shrink it a little. There's a little opportunity here. Looks like we might be able to get it about an inch or two out, but that is not the point of what I want to show you today. What I want to show you today is I want to get a sine wave coming out of this thing, and I want to try to put it through its paces. I want to see if we can load down the inverter a little bit. Yeah, because that's okay. I might be an idiot. I might have literally forgotten to connect both power leads. That is okay. We all have those moments. Light bulb is on. I would expect that to trigger. Oof. This is exciting. Okay. Load test the first. Yes. That's awesome. Our DC link dropped. So it looks like the input impedance of this system is preventing it from functioning correctly. That means there is only two things that we can do. Thing the first, I need to go get my power meter so we can measure the output power. The second thing we need to do is connect this straight to the batteries. Oh, that's awesome. Maybe we should get a fan going. Kind of blowing across the heatsink too. Let me grab a fan. System is powered from the battery pack. Hey, this is now or never time. Cross your fingers and hope for the best, because there we go. We're getting 57 watts out. That's awesome. We're getting 57 watts out. Okay, I want to go get more loads. Yeah, that was like nameplate rating, right? This was a 60 watt bulb. Yeah, that's excellent. So I had come to the conclusion that I had never planned for this thing to actually work until I found this gigantic light bulb. This should be a 300 watt load. So an order of magnitude more power. And the only step I have above that, this giant 300 watt light bulb is actually about 2,000 watts, which is my toaster oven. So basically, it's gonna go from 0 to 100 real fast. Yeah. But we gotta test it somehow. That snap when you plug in the batteries is pretty awesome, that inrush current. Okay. Nope. Gotta reset the thing. Now we might have tripped the current limit. There is a current limit that comes on. And I actually don't remember what that's set to in software. We might have tripped the current limit. So I switched off the supply. And put that to watts, and we're gonna kick on the bulb. Yeah, I think we're tripping the current limit. Yeah. I'm gonna go either turn that off in software or turn it up. We're gonna do kind of the same routine where we'll power it on and then we will tweak the limits. Okay. 3, 2, 1, go. 1.2 watts. Yeah, boy. 200 watts out. Yup. That is what awesome looks like. Battery module going strong. Inverter Daughtercard does not care. Oh, that's fun. Oh, that is fun. We've got to restart the mainboard micro, but that's okay. Leave no stone unturned. I have nowhere to put this. The bench is full. Oh my goodness. Okay. Yep. 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 This is just gonna need to happen. Oh boy. Okay. Oh boy. Oh, come on. Yep. Alright. We're just gonna set it on top of stuff. That's fine. Yeah, this is fine. Everything is fine. Okay, we're gonna set it to toast. We're gonna set it to toast. We're gonna turn it on. The light bulb is being unplugged. The toaster oven is being plugged in. Actually, you know what? Let's turn it off so we can get the power meter on before we kick on the load. Turning it on. Kilowatt meter. Says half a watt. Okay. Something blew. Something gave. And now that I think about what I'm doing with my life, I don't know if a 7.5 amp fuse is sufficient. That would, yes, the fuse is what we blew. Yes, of course. Yes, of course. And there appears to be some kind of issue where when that fuse blows, the other fuse blows as well. So I'm not sure. Or is it if one fuse power's cut from, wait. No, because we shouldn't have. Ooh, the transformer's actually warm. So is the inductor. Our heatsink's actually warm. We pumped enough power to this thing to make the heatsink warm. Not the other one though, just one heatsink. Okay. Sorry, I'm getting giddy. I am so excited. I am shaking. I'm so excited. Alright, this camera better be rolling. Scope capture appears to be... Scope capture is not working. Okay, scope capture is working. It appears that everything is ready to roll. We blew the crap out of that 7-amp fuse. Alright. Guys. Ooh. I didn't see exactly what blew, but I'm gonna need to watch that footage back. Visible sparks. Visible sparks. I think that were the FETs. I think that was the FETs on the oh. Oh my goodness. Okay, so I don't know if you guys saw that on the scope capture. I was looking at 15 things at once. Hopefully you saw that. Oh, my heart is pumping. That's amazing. Nothing like the smell of ozone in the morning. So that was a hard enough load. That was an intense enough load. Oh my goodness, that smells so bad. Oh, that smells terrible. The smell of ozone has been replaced by the smell of burning silicon. I think we might need to upgrade the FETs in the battery module in order to get this thing up to 1,000 watts. Transformer's not notably warm. Well, the windings are a little warm. Output inductors are cool to the touch. These inductors are also cool to the touch. These FETs are a little warm. This heatsink is quite warm. That was awesome. Anyways, yeah, gotta push things to its limit, right? Oh, that was so cool. If I saw that right, it's like we were browning out the square, or the sine wave turned kind of squarish, because as we would increase the power cycle by cycle, the output of this converter started to fail, the FETs got hot, and then eventually broke down because we exceeded the TJ max rating of the FETs. That's what I think just happened. Oh, that is incredible. That is incredible. I wish we had the DMM hooked up so we could see the bus voltage, but I am confident this thing is securely, surely broken. We've got some more FETs. I can replace it, get it up and running, but this was awesome. I hope that you enjoyed this video. We exceeded the previous limit of the UPS. We have powered the load that broke the phase 1 UPS. More than 100 watts out. More than, I think it was like 150 is what it was measured. Tried to go for 1,000 and well, we didn't quite get there, but that's what happens when you increase your load by an order of magnitude. I hope that you liked this video. Hit that like button if you liked it. Get subscribed if you want to see more awesome content like this. We're going to have some sweet educational videos coming up, so make sure you do not miss those. It's going to be a fun time. Most of all, thanks for those who support us on Patreon. Thanks for watching this video, and thank you for staying till the end. Yeah. That's about all I can think of right now. So, hope you enjoyed. Bye.